Hey guys, today we're going to go through an Ansys Fluent tutorial. In this tutorial, we're going to look at a simple forced convection problem, hopefully give you some insight on how to set this up and adapt it to your own issue. To do this, we're going to look at a simple problem statement. So we can go through the problem statement now. Problem statement says that we have an electronic chip that is attached to a circuit board with a total design power of about 1 watt. The electronic chip can withstand a maximum package temperature at 50 degrees Celsius. Onto that package, we're going to attach an off-the-shelf heatsink, and we're going to supply the heatsink with 1 meter per second of airflow. And so we have some questions here. These questions kind of mimic what you'd see in an engineering environment, things that you may want to solve for when you're looking at a design like this. So the questions are going to be, will the heatsink and the airflow provide sufficient cooling for the chip? What will the maximum package temperature of the electronic chip be under these conditions? And what will the downstream or the average temperature of the air leaving the heatsink be? So no further ado, let's hop over into Workbench and we'll get this problem set up. So now that we're over in Workbench, we can start setting up our problem. So when you open Workbench, you're going to be shown this screen. You're going to have your project schematic here and then all your analysis systems on the left. First thing you're going to want to do is always save your project. So in this case, I saved it as forced convection, so we're good to go. We're going to pull over the fluid flow Fluent system analysis here. We can drag and drop it into our schematic and we can start doing our analysis. There's a few different geometry tools that you can use in Ansys Workbench. Those are Design Modeler and Spaceclaim. To change between the two, you can right click and either select a new Design Modeler geometry or a new Spaceclaim geometry. For this example, we're going to build our part in our analysis in Spaceclaim. So we'll click on new Spaceclaim geometry and we'll get that fired up. Now that we're in Spaceclaim, we can start drafting up our example problem and create our domain for our analysis. To do this, we're going to start by creating the chip. So we'll select the rectangle tool. We'll lock it in at the origin and we'll make the chip 10 by 10 millimeters. We can pull this to give it height by clicking the pull tool or clicking P on the keyboard. And we'll pull that up 1 millimeter. Next, we'll create our heatsink. So we'll go to the Design tab, we'll click Sketch, and we'll sketch right on top of that chip that we just created. We can use this little Cartesian coordinate in the bottom left corner to change our view. So we'll click on the Y so we can look top down. Just give ourselves a better reference frame here. And we'll create another rectangle, same size, so another 10 by 10 millimeters. And deselect our chip underneath just so we're looking at our heatsink. And again, we'll click Pull. And we'll pull up the base of our heatsink. We'll make that another 1 millimeter. So now we can create the fins on top of our heatsink. To do that, we can go to Sketch again. So we'll go Design, Sketch, Sketch right on top, and go Rectangle tool, select the corner, and we'll make the fins 1 millimeter, extending the full length of our heatsink. We'll pull those up, and we'll pull that 10 millimeters. So now we have one of our fins. A simple tool to create the rest of our fins, they're going to be using the rectangular pattern tool. So to do this, the first thing we're going to want to do is essentially split this first fin off. So we'll go to Design, we'll go to Split Body, and we'll select our heatsink and then the top surface where these fin and the base of our heatsink intersect. And we'll essentially split that off as a separate solid body. Now what we can do is use the rectangular pattern tool also under the Design tab, and we can select our fin in the browser. Click this arrow for the edge and we'll select the edge that we wanted to pattern across. And you'll see this red arrow. We can use this to flip essentially the direction of the pattern. So for the pattern, we're going to go with 4 fins. We're going to make the spacing of those fins 3 millimeters. So that will give us 4 fins with a millimeter gap in between. So we'll click the green check mark, and now you can see we have our 4 fins created. We want the heatsink to be one body. So to do that, we can just combine and select the base of our heatsink. So we can either hold Control on the keyboard or select this merge body option here. So we'll select merge body. We'll click select. We don't want to save the changes to this component, so we can just click no. Click no again, keep clicking no. And so now we have one body that essentially captures our whole heatsink. So now that we consume the pattern, this is just going to be empty in the browser here. So we can go ahead and just delete that just to keep our model clean. And we can turn our chip back on. And just to make sure we can see everything independently, we're going to triple click on our heatsink. We're going to right click and just change the color to a gray, just to give us some differentiation to know that they're two separate parts. So now we can see we have the chip and our heatsink, and that's going to be all the solid components we need for our analysis. So the next thing we're going to want to do is create the fluid domain around these parts. To do that, we can go to the Prepare tab, we can select Enclosure, and we can drag and select both of our components. We're going to uncheck Symmetric Dimensions here, so we can change all the dimensions independently, and we'll start changing some of the dimensions. So first, for the inlet, we're only going to make that about 15 millimeters, because we don't need that much airflow tracking on the front side. On the back, we're going to make it a little bit bigger so we can really capture the airflow as it moves out and make sure we aren't affecting any of the numerics close to kind of the region of interest. So we'll make that 50 millimeters. Next, on the left and right side, we can make these 10 and 10. And then we can do the same on the top. We'll also do 10 millimeters above our heatsink. And on the bottom, since this chip is going to be attached to a PCB, we're going to bring our enclosure right up to the bottom of our heatsink. So we'll just make that 0. Once we're happy with our enclosure, we can click the green check mark and we'll now get the enclosure. The error here that we're getting is essentially saying that one of our bodies is protruding from our enclosure, which is okay because we want that heatsink to be at the same level at the bottom of our enclosure. So now that we're happy with our geometry, the last thing we're going to want to do before we move into meshing is go over to this Design tab, click on the Design, and you'll see a bunch of properties down here. The one property we're going to want to change is this shared topology, because we're going to want to couple the walls between the enclosure and the solid part. So we're going to want to share that topology. So we'll go to the drop-down menu and click Share. And I'll show you how this shows up in meshing and analysis later on. So now that we're back in Workbench, you can see this refresh button here under the mesh node. And it's essentially saying that there's a geometry being transferred from Spaceclaim and the meshing is ready to accept that geometry. So we'll go to the mesh, we'll double click, and we'll open up the meshing tab. So now we're in meshing, and we can do a few checks here before we go on with our project. We can make sure that there's no connections under this connection tabs here. Make sure that our topology is shared correctly. So no connection showed up. Everything looks good. It means that the geometry was shared correctly. The next thing we're going to want to do, which is very important, is to name all of our faces and bodies. To do this, we're going to select the face select here. And we're going to start naming the faces according to our analysis. So this front edge or front face, we're going to click N on the keyboard and we're going to call it inlet. We'll do the same on the back here. We'll select that face, hit N on the keyboard and say outlet. Now for the bottom side, since this is going to be on the PCB and just going to be a solid wall, we can select the bottom edge of the enclosure, and we'll also select the bottom edge of the chip since they're going to have the same boundary conditions. And we'll click N and call that bottom wall. Now for our other three sides, what we're going to use is a symmetry boundary condition. And we can explain a little bit more about that symmetry boundary condition as we get into Ansys Fluent. So we'll select those three edges, we'll click N again, and we'll call them symmetry. And it's important to name your faces in meshing what they're going to be in the simulation. So if you call an inlet, when it gets carried over into Ansys, it will automatically set that to an inlet in Fluent, and it will save you a little bit of time setting up the problem. The last thing I like to do as well is also name all of my bodies. So I'm going to select the body tool up here. I'll select the enclosure, click N, call this enclosure. I'll do the same for the chip. So I'll select the chip, call it chip. And then we're going to right click on the enclosure and click hide body just so we can look at our heatsink. And we'll do the same for the heatsink. So we'll select it and call it heatsink. The next thing we're going to want to do is start meshing. My preferred workflow when I work in meshing is to start by just creating a mesh with the default numbers that are given by Ansys. So you can click on the meshing tab and go ahead and click update. And what this essentially does for me is it checks to make sure that the geometry will mesh at all. If there's any errors, so if you have overlapping geometry or weird sharp edges or any other geometric errors from Spaceclaim, this initial mesh will capture that error and kick out an error. So you don't spend a bunch of time refining your mesh before doing that. So we can see that the mesh was created successfully. You can see it created a very, very coarse mesh with the default numbers in there. So we're going to want to refine this a little bit. So we'll start by just clearing that mesh. So we'll right click on mesh and click clear generated data, just so we can kind of start over with our meshing. What we're going to want to do is we're going to start by working out from our chip and working out to our enclosure. So we'll start by refining our chip here. To do that, we can select the whole body. We can right click and go to insert and click sizing. And this will allow us to set an element size for this entire body. So what we're going to do for that is we're going to set this to 250 micron. And we can check that by right clicking and clicking generate mesh on selected bodies. And if we click back on the mesh here, you can now see graphically what our mesh will look like. So you can see we created a mesh on our chip. We have 4 elements in the vertical direction, and it created a structured mesh. So just structured rectangular prisms for that mesh, which is great. So we're going to give the same treatment to our heatsink as well. So we'll right click on our heatsink, we'll go to insert, we'll go to sizing, and we'll give that the same sizing of 250 microns. And again, we'll right click on that, generate mesh on that body. So the last thing we're going to want to do is mesh the enclosure. So we can show all bodies, show the enclosure again. And we're also going to do a sizing constraint for the enclosure. So we'll go to insert, sizing, and we'll set the element here. So for this larger domain, we're going to go a little bit bigger on the mesh elements. Let's go to about, we'll set the maximum size to about 3 millimeters. And one other setting we're going to want to turn on here is the capture proximity option. So we'll click yes to that. And we can leave the default numbers in here for the time being. And we'll go ahead and generate the mesh on that as well. And we can look at that. And as you can see, we have a pretty coarse mesh here. It does have some refinement as it moves out from our smaller mesh elements on the heatsink and chip, which is great. This mesh is definitely a little bit coarse, but for the purpose of example, I think we're going to go with it. So some other things we can check before we move into Fluent is both the quality of our mesh and the size of our mesh. To do that, again, just click on the Mesh tab, and you can come down here to the details, and we can check a few different things. So the first thing I like to check is at this bottom statistics tab. If you expand that, it will show you the number of nodes and the number of elements that you have on your entirety of the mesh. So right now we're at about 440,000, which is pretty good, pretty simple mesh, but great for this tutorial. The other thing you can check graphically is the mesh quality. And to do that, you can go to the top and look at this display style, and you can click on this drop-down menu and essentially select all these different mesh metrics. So the first thing we're going to look at is skewness, which is a great metric to check for the quality of your mesh. And as you can see, when you select that display style, it will overlay the quality of the mesh onto every part. And we can look at the scale here and check out our minimum and maximum skewness. And as we can see, our maximum skewness is about 0.77. For skewness, we want to be below essentially 0.9 is kind of a good benchmark to aim for. So at 0.77, we're looking great. The next thing we're going to want to check is orthogonal quality. We can check that as well. And for orthogonal quality, we essentially want to be above 0.1. And in this case, our minimum is at 0.22, which is also great. And the final one I want to check for this mesh is element quality. So it's the same kind of scale as orthogonal quality where we're looking for our minimum value. Anything below maybe 0.15 or 0.1 is acceptable or unacceptable. So at 0.25, we're looking great, which again is perfect for this simple mesh. So now that we're happy with our mesh, we're happy how it looks, we're happy with the mesh metrics, we can now take this and move into Ansys Fluent. So now that we're back in Workbench, we can see that under the meshing tab, we have a green check mark, which means that our mesh was transferred successfully. And our setup tab now has this refresh icon, which means it's ready to accept our new mesh and start our analysis. We're going to double click on that setup tab. This is going to bring up the Fluent launcher. Some settings we're going to want to check here is double precision. And then we can also set the solver processes. So essentially the amount of CPU cores that you want to use. In this case, we're just going to use 4 since it's a pretty simple mesh. And we can go ahead and click start and hop right into Fluent. So now that we're in Fluent, we can see that our mesh was carried over successfully in the graphics window here. And we can check the console and just make sure that we didn't get any errors. Most critical errors are going to be highlighted in red, so everything looks good here. And the first thing we're always going to want to do when we bring a mesh into Fluent is look at the mesh check and check the mesh quality. So we'll go ahead and click perform mesh check. And this will essentially give us some volume statistics and some face statistics. And if there's any errors like small faces or bad cells, it will come up in this mesh check. So everything looks done. So we're good to go. We can also check the quality here. We'll evaluate mesh quality. Similar to what we were checking earlier in the meshing step, it will give us a minimum orthogonal quality. So we're at 0.226 e to the negative 1, which is great. And also the maximum aspect ratio, which is also looking great. So once we check both those things and we're confident that our mesh is ready to go, we can start with our modeling setup. So we'll start here at the general tab. In our case, we're going to use a pressure-based solver. We're going to do a steady state analysis. So we can change that to transient here if we want to do a transient analysis. And in our case, since we're looking at forced convection and not natural convection, we can leave gravity off. Since it's not going to actually make that much of a difference to our numerics here. The next thing we're going to want to do is look at the modeling tab. For our case, we're going to want to turn on energy since we're looking at heat transfer. And then we're going to change our viscous mechanism to laminar since we're not looking at turbulence because our flow is so low. We'll click OK. The next thing we want to do is look at the materials tab. The default material or fluid material that you're going to see is air. We're going to keep that on for now, and we can double check the properties of that air. For our case, since again, we're not doing any natural convection and our temperature change is going to be minimal, we're just going to leave the density to a constant value. We can go ahead and close out of that. So for our solid materials, aluminum is going to be the default that comes up, but we're also going to want to add copper, which we're going to use for our chip. So to do that, we can double click on aluminum. We can double check the properties of our aluminum here. We can just use all the default values. And then to add the copper, what we'll do is click on this Fluent database. We will go to this drop-down menu and change to our solid materials. And we'll go ahead and select copper. So what you're going to want to do is select copper and then click copy. And as you can see, the copper now got added to our simulation. So we can double check the properties of the copper. Just make sure they're all okay. Again, we're just going to stay with the default consistent values for all of these. So moving down the line, we're going to go to cell zone conditions. In here, we can change essentially our fluid and solid zones. So for our enclosure, we can make sure that it's air, which is going to default to, so everything looks okay there. We'll click apply. For our chip, we are going to want to change the material value to copper. So we'll go ahead and click copper here. And the other thing we're going to want to do here is add our source term. So our 1 watt of heating on our chip. So we can check the source term. We can go to source terms here. We can go to edit, add 1 source term, and we're just going to use a constant value. So the value here for a volumetric heat source is going to be in watts per meter cubed. So what we're going to want to do is we'll open up the calculator quick. We'll change this to scientific and we'll go 1 watt and we're going to divide it by our volume. So in this case, we have a pretty simple volume. We know that it's 10 millimeters by 10 millimeters by 1 millimeter. So we'll type that in, and what we get is essentially 10 million watts per meter cubed. So we can copy that, we can put it right into our value here, and click OK. And we'll click Apply. Now we have our volume source captured. Close out of that. We can double check our heat sink here. It's going to default aluminum, but if we want to change the material of it, we can also change it here, but we'll leave it as aluminum for this. Click Apply. So the next thing we're going to want to look at is boundary conditions. And so here is where you can see that our naming conventions really helped us with our setup here. So our inlet is already denoted as an inlet. Our outlet is already denoted as an outlet. And what we set as a wall and symmetry are already set as wall and symmetry values, which is great. It saves us a bunch of time with essentially applying those different boundary conditions. So for our inlet, we're going to use a velocity inlet. We'll set that velocity to the velocity of our problem, which is 1 millimeter, or 1 meter per second, sorry. We can apply that, and then we can double check our thermal condition here. So for our case, our air temperature, initial air temperature is going to be 20 degrees Celsius, which is 293 degrees Kelvin. So we'll click Apply. And if you don't want to work in Kelvin and you want to work in Celsius, you can change that by changing the units by going to the Domain tab, selecting Units. You can scroll down here and find your temperature. Temperature, and we can change that from Kelvin to Celsius. So we'll go ahead and do that now. So now when we look at any of the thermal tabs, they'll be in Celsius. So we can actually get this a little bit more precise and set that right to 20 degrees Celsius. Click Apply. For our outlet, it's going to default to a pressure outlet. We're going to go ahead and change that type to an outflow since we're just doing an open airflow environment. For symmetry here, the symmetry boundary condition, you don't have to do anything. It's just a kind of numerical setting, so we can leave that as is. And in the wall conditions here, we can change some of the values here. So for the bottom wall, in our case, we're just going to keep it as an adiabatic wall. So there's going to be no heat flux through that bottom surface. But if you did want to increase the accuracy of the simulation, there probably would be a little bit of heat loss through that PCB. So you can set that as a heat flux value here, or you can also turn on a convection value or set it to a fixed temperature for a certain problem. You can change all that under the wall zone conditions here. But for our case, we're just going to leave it adiabatic and leave this heat flux value to 0. The other thing we can change in here is, or other thing we're going to want to change in here is since we changed the material of our chip and our heatsink to be different materials, we're going to want to split the interface wall essentially between those two layers. To do that, we can look at the internal and we can see our interior chipped heatsink here. If we want to display it, we can display it on the actual graphics window here. So we can see that's the interface between our chip and our heatsink. And we're going to actually want to change this to a wall. And what that will allow us to do is if we did want to add in any contact resistance between the heatsink and our chip, so you're using a thermal compound, or if you have a thick layer of solder or something, you may want to add essentially a contact resistance between those two layers. In our case, we're just going to keep it as a coupled wall. So it's just going to be one-to-one heat conduction and essentially no heat transfer resistance between those two materials in our setup. So we can close out of that. In our solutions tab, it's going to default to a lot of variables here. The variables that it defaults to are essentially the most highly accurate variables, I'd say. So we can change our pressure velocity coupling. Simple is a quick and common pressure velocity coupling scheme to use. In our case, we're going to use coupled for just a little bit higher accuracy. The other thing we can change here is the gradient discretization. We'll leave it on least squares here. Again, a little bit slower, but a little bit higher accuracy. Same thing with the pressure, momentum, and energy. We're going to leave that all on the default values of second order. The last setting we want to look at here is the pseudo time step method. So what we're going to do is use the pseudo time step method, which relaxes some of the numerics and uses an artificial time step to give us a more robust, easier to converge problem for heat transfer. So we'll leave that on global time step. The next thing, we can look at our controls here. Under controls, you can see we have our pseudo time step relaxation factors. We're going to leave those on all the defaults. You can change some of these values depending on the exact simulation that you want to set up, but for our case, these default values should be okay. The next thing we're going to want to do is create a report definition. And what this allows you to do is essentially monitor some of your terms as your equation is solving. So the one thing that we're going to want to monitor is the temperature of the chip. So to do this, we can right click on report definitions. We can go to new and we can look at a volume report. And we're going to take the volume average and we can give it a name. We'll say chip temperature. We'll just leave it chip temp. And we can select report types of volume average. We're going to check the temperature and we're going to look at the static temperature and we're going to select our chip cell zone. We can report both a file, which will export a CSV file of this plot, and we can also report a plot. In our case, we don't really care about exporting the file, so we're going to uncheck that and just leave a report plot. So click OK. The other thing we can monitor while we're solving is we can look at the area weighted average of the outflow temperature. So we can look at outflow temp. We'll go area weighted average and we'll go to temperature, static temperature, and then select outlet. And this will essentially let us know the average temperature of the air flowing out of our domain. Again, we're going to uncheck report file and click OK. So everything else here looks okay. We're not going to do any mesh adaptation or register any cells. So the next step is to initialize our mesh. There's two options when initializing. There's hybrid initialization and standard initialization. For our case, we're going to go with hybrid initialization. So we can go ahead and click initialize. And you will see it does a simple iteration here. So in this case, it goes through 10 iterations. And it is giving us a warning here that the convergence tolerance did not reach the threshold that it's looking for, but that's okay for our instance. It's common that the hybrid initialization does not always reach that threshold that it's looking for, but that should be totally okay for our case. We're going to go ahead and run this calculation. So in the Run tab, there's one final check that you can do, and that's this check case option. So we're going to go ahead and click that. And as you can see, it says no recommendations to make at this time. If there is an error in your setup, this may catch some simple things, like if you misset a value for material property or something, it may give you a recommendation here. So it's always a good check before you solve. For solver settings, we're going to leave the fluid timescale and the solid timescale. We're going to leave those at 1 for the time being, just the default value. And the only thing we're going to want to change in this window here is we can change the number of iterations that we're going to want to solve over. So we're just going to go with a value of 500 to start. And for export, we're going to want to make sure that we select our data file quantities that we want to export. So you can see all the standard qualities that it's going to export to CFD Post. There may be a few other ones that we want to add. So maybe we might want to add static pressure, might be interesting. If we scroll down here, we can export the volumetric energy source, maybe the total temperature, maybe some of these wall temperatures would be good to look at. Another one really important for heat transfer is also going to be the heat flux coefficient. So we can set the total surface heat flux, the surface heat transfer coefficient, and the wall adjacent heat transfer coefficient. And also the new set number is something that would be good to export. So we can select those as well to make sure that those export the CFD Post. You can select all of these if you want to make sure that you have all the data captured, but the more you select here, the bigger your data file is going to be in the end. So I think we're happy with those. We can click OK, and we can go ahead and start running our calculation. So we'll just go ahead and click calculate. So now that our calculation started, one of the most classical ways to essentially monitor your convergence of your CFD problem is looking at the residuals. And these are essentially, you can think of as the error of your numerics. And you're always looking to minimize the error of the residuals. So you're always looking for these lines to go down. So you can see that these lines correspond to the continuity, the XYZ velocity, and then on the bottom here, our energy term. So we can see as this goes through every iteration, those are slowly going to start moving down as our solution starts converging. The other thing you can see here is we have a plot for our chip temperature, as well as the outflow temperature that we set earlier. And as this solves, you can see that these lines are changing. And these are another great thing to monitor and make sure that your solution is converging. So don't always rely on the residuals. If the residuals go down below the threshold that you're looking for, it is always a good sign, but it's always best practice to also check some of your numerics to make sure that the actual value that you want out of your simulation is also converging. So we're going to give this some time to run, and we'll check back in when it's finished solving. So when our solution converges, we'll get this little pop-up menu that lets us know that our calculation is complete. And if we look in the console here, we can also see that our solution is converged. By default, Fluent uses the residuals as the convergence criteria. And by default, it sets all of those to E-3, 1E-3 as the convergence criteria. We can change those by going to the Solution tab here and clicking on Residuals. And we can see here our absolute criteria for convergence. We can uncheck these if we're not interested in, the XYZ velocity, and maybe we're just interested in the energy value. We can leave that as our only convergence criteria. And we can also change these values if we want to let the solution run longer or converge kind of to a lower residual level. But for our case, we'll leave it at the default, and we'll look at our converged solution here. So again, the other thing to check is our other values. So we can look at our chip temp. That converged nicely to a nice flat line. Same with our outlet flow temperature, nice and flat. You can see it kind of ramped up in the start and then converged to a nice value. So it looks like our solution ran well and we got some good data out of it. So the next thing to check for your results is to look at your fluxes and make sure that your flux values also look okay. So we can go to this fluxes tab under results, and we'll check two things here. We can check the mass flow rate. So we'll select really just the inlet, outlet, and symmetry conditions, but we'll just select all just to be thorough and click compute. And you can see that our net result is about 3e to the negative 19, which is great. It means that there's kind of no residual mass flow in our system, and we had some really great convergence. We can also check our total heat transfer rate here. So we'll compute that again. And you can see that our convergence or net result of wattage is about 0.0002, which is a little bit high. We could probably let this run a little bit longer and converge a little bit better, but for our case, it's going to be okay. If you see very high values here, like, maybe 0.1 or even close to your inlet source, it means that you're getting essentially bad convergence and poor numerics. And there's essentially heat being generated where there isn't supposed to be heat generated. So this is always a good check to make sure that your solution converged correctly. So again, we're back into Workbench now, and you can see that both our setup and solution have green check marks, which means our simulation ran. We have results, and those are ready to be post-processed. And our results tab currently has the little refresh icon. So we're ready to hop into CFD Post. So we'll double click on the results tab, and that will put us automatically into CFD Post. So now that we're in CFD Post, we can look through some of the more specifics that we were looking at and making sure that our solution gives us the data that we're really looking for. So to do this, we'll again go to the contour tool, which is this little icon here. We'll select that. We'll make a heatsink temp contour. And again, we're going to select the wall of the heatsink. And again, we can change that to temperature. We'll range it by global, and we can change the number of contours here. We can do about 50 contours and click apply. And as you can see, again, this is being graded by the global temperature. We can change that to local to get a more usable plot. Click OK. And you can see a great temperature plot here of our heatsink. So hottest on the bottom, and you can see as it's dissipating heat as you go up the fins. We can change our scale here to Celsius again. And we can do that by going to the variables tab, selecting our temperature output. and changing that to Celsius, so it gives you a little bit more usable plots. The other thing we can do, if we want to take this out of scientific notation, is we can hop back to the outline tab here. We can look for our legend. We can change the appearance, and we can change this from scientific to a fixed, which when you're communicating results, it's definitely easier to look at non-scientific notation, especially when we're looking at, relatively low values. So that gives us the temperature of our heatsink. We can do another plane here. So we'll do location. We'll add a plane and call this the YZ plane. Okay. So we'll make a plane in the YZ direction. We'll offset it to the midpoint of our domain, which I believe was 0.005, if I remember correctly. We'll click OK. Yep, so that'll give us our midpoint plane right down the middle of our heatsink. And now we can plot some contours on this plane, so showing exactly what we showed in Fluent. So we'll go to contour again. We'll call this YZ temp. And we can plot a temperature plot. We will select the YZ plane that we just created. Click OK. We'll leave this on global for temperature range, and we'll increase the number of contours again to 50. Click apply. And we'll turn off our plane just so it graphically looks a little bit better. And we can also turn off our heatsink here, and we can again look at our plot here. So another great plot, you can see as the air heats up as it transfers to the heatsink and moves out of the domain. So now we can keep plotting some of these variables and look at these nice rainbows, but usually in an engineering world, you're really concerned about explicit values. So if you remember back to our problem statement, one of the values that we were really interested in is what was the maximum temperature of our chip, because we knew that it could only withstand 50 degrees Celsius. So the best way to get explicit values is by using the calculator tab in CFD Post. And what you can do here is you can go to the calculator tab, we'll select function calculator, and we can start calculating some explicit values from our simulation. So the first one we're going to look at is we're going to take a volume average, and we're going to look at the chip. So we can select our cell zones here. We're going to look at the chip to start, and we're going to look for the temperature. And we can click calculate. And what we can see here is that our average temperature of our chip is 317.741. So it looks great. We can also change this from a volume average to a maximum value. So we can look at the maximum point on our package and click calculate again. And that will give us 317, a little bit higher than the average, but not much higher. And so looking at this, what we know is that our chip was able to stay below that 50 degrees Celsius threshold that we set, which is great. It means that our design is working and our input conditions are going to be great. The other useful thing to use in CFD Post is the chart tab. So what we can do with the chart is we can plot some variables through our domain. And these are, again, good ways to display data and good ways to communicate that data of your simulation. So before we set up a chart, we're going to want to set up some locations that we want to look at in the chart. So one really interesting location that I think we may be interested in is we want to look at the air temperature as it moves from the inlet through to the outlet, what that temperature looks like, what the air temperature looks like as it moves through that point. So to do that, we're going to create a line across the entire domain. So we'll create a line here. We'll call this the midplane line. So the method that we're going to use here, we can select 2 points, and we'll make a line that extends from the inlet all the way through to the outlet. So these points here are going to be your X, Y, and Z component. So in this case, we're going to want the Z to go all the way positive. So it starts at the inlet. And we want our second point to be all the way negative. And then we'll use the X, Y component to essentially give us the direction of our line. So we're going to want to set our Y value to essentially the mid plane, which is going to be at around, say about 5 millimeters. So we'll set that for both points. And then we're going to set the X coordinate as well, which is also going to be at 5 millimeters from the origin. And we'll click apply. So what you can see now is this is giving us a line straight through the domain that goes right between the two middle fins of our heatsink and right through the enclosure. And we can increase the number of samples, which will give us a better chart. So we'll increase that to 100, click apply. And so now we can add a chart and essentially plot the temperature along that line. So we'll click the chart tool. We'll say, let's call it midline temp. Okay. So here in the chart tool, we have a few different options. We can choose a line plot, scatter plot, a transient or sequence plot, and a histogram. In our case, we're going to go with a line. We'll give it a title. We'll say air temp along midpoint or midplane. We'll go over here to the data series tab. And so we can set series of data. We can set a location. We'll pick our line that we created. And we can set our X and Y variables. So for our X axis, we're going to want to make that the Z direction, since our Z is our the axis of the plane that we're looking down. And then our Y, we're going to look at the temperature along that line. And we can change some of the line display and chart display if we want, but we're going to go ahead and just apply that. So what you can look here, you kind of have to flip it around in your mind. The way that we set up the equation is the Z direction is essentially positive, so in front of the heatsink, and the Z negative is essentially behind it. Our chart is going to be a little bit inverted, so you can kind of flip your brain a little bit. So what you can see here is our airflow is coming in at 20 degrees Celsius. As it goes to the heatsink, it spikes up to about 31.5 degrees, and then slowly tapers off as it kind of mixes with the rest of the ambient air as it trails off. The other thing we can do is we can add some more series to this. So we can create another line. To do that, we're just going to duplicate our midplane line here. So let's go to duplicate. We'll call it midpoint line 2. Okay. And if we go back to our graphics window here, maybe we want to look at directly above the chip, and we want to look as we go a little bit higher up, so we can add another line. So I'll move this up in the Y direction a little bit. Let's maybe go to about 8 millimeters, apply, and you see we can get another line here. And we can hop back over to our chart and go to data series. We can add a new data series. We can label that if we want to, but I'll just leave it as series 2. And we'll now select our second line. And so we'll apply that as well. And now you can see that blue line is our second data series, essentially the next line up. What we could do if we wanted to export this data in a kind of a logical fashion is we could put a series of lines from bottom to top, so we get a good kind of span of the airflow as it transfers through that heatsink. The last thing we want to check, going back to our problem statement, is we want to know the downstream air temperature, what it was kind of average temperature in case there's maybe another component, another heatsink behind this, and we want to know how hot it's going to be. So to do that, we can go back to our calculator tab here. We can go to our function calculator. We can look at the, let's look at maybe the maximum value, and we'll look at the outlet. And so we'll look at the maximum temperature outlet as the air temperature leaves the domain. So the maximum outlet temperature as the air is leaving the domain is about 302 degrees Kelvin. So that's a good sense of what our air temperature kind of downstream is going to look like. We can also do an average by going to area average. Again, looking at the outlet, looking at the temperature. We can set the direction, just keep it on none, and click calculate again. So we'll get an average air temperature leaving our domain at about 295-ish degrees Kelvin, which again is great. We can take that data and we can, if we have another heatsink maybe in series with this one, we can now use that as our inlet condition to our next simulation to make sure that our next chip down the line is getting adequate cooling. So the last tool that I want to show you is maybe not as applicable to this specific problem, but is another interesting analysis tool to look at, which is the isosurface. So creating an isosurface allows you to essentially map a surface related to some certain parameter. So in our case, maybe we want to plot a isosurface at a temperature of, let's say, maybe 300 degrees Kelvin. And we'll click apply on that. And essentially what that gives you is a really cool plot. And it essentially places an isosurface on the line that is 300 degrees Kelvin. So we can turn off some of our other analyses here and just look at the isosurface. And this kind of gives you a good sense of, you can look as our airflow kind of goes through our heatsink and then travels out. You can see that region of about 300 degrees Kelvin. And again, this is good to look at if you're looking at an enclosure or something else. You can get a sense of, where the hot air is traveling, how big the kind of volume of hot air is and stuff like that. And this problem is maybe not as applicable of an analysis technique, but is another good tool to use for certain analysis. So with that, I think that's a pretty general overview of CFD Post. We can keep going down with analysis and keep solving, making some more colorful plots and stuff. But I think for our case and our problem statement, we got the data that we needed. We have what we need to communicate to the engineering team or whoever else we're talking about. And I think at that point, our simulation would be complete. So with that, we now have the beautiful 5 check marks all the way down the line, which means we successfully created our geometry, created our mesh, analyzed our problem, and analyzed the results. And we can now take that data, move it into a different simulation, feed it back to the engineering team, maybe go back and change some of our parameters. So we can look at changing the inlet temperature. We can look at changing the size of the heatsink, maybe the total design power, see how much we can force into that chip before we exceed the maximum temperature. If we wanted to do that, you can quickly duplicate this. So we can right click on the top Fluent Flow kind of title here, click duplicate, and this will essentially duplicate this setup that you have into a new setup. And this will allow you to run it again. It will save your geometry and mesh and allow you to rerun your solution with maybe some new parameters. If you want to go back, you can change the geometry, but always retain that initial setup you had. The other thing you can do, if you want to just maybe save the geometry, you can pull over another fluid flow analysis. You can take the geometry and you can pull it right into meshing. So you can go right into meshing, or you could pull it into a geometry tab if you want to do that. So there's a lot of usability that you can do in Workbench when you want to kind of elaborate and look at maybe some design of experiments or other things. I'll have a video a little bit more detailed on using the parametric function in Workbench coming a little bit later. Overall, this is just a really general look at a forced convection problem. I hope this helps you set up your first problem, and you can run and adapt this to all of your engineering needs. And if you have any questions, please leave them down in the comments. If you have selection or suggestions for future topics, please leave those in the comments as well. I try to respond to as many comments as I can and try to answer as many questions as possible. So let me know if you have anything. Without further ado, I would like to thank you for watching and keep your eye out for more videos coming in the future. Thanks.